since then. But it was a very different talk, very different project. So even if you happen to be there, you will see something new. Can you see my screen all right?
Yes, we can see it.
Okay, awesome. So welcome everyone. I would like to show you how you can use your .NET skills to create computer chips. Well, it's not quite that exactly, but I hoped I already piqued your interest. Because I would like to show you our open source Hastlayer project. But before even that, a little bit of introduction of who I am, where I'm coming from. The company behind Hastlayer is Lombic Technologies. I'm one of the co-founders there. And day-to-day, we actually do .NET web development with the ASP.NET Core content management system called Orchid Core. Has anybody actually used Orchid Core here before? I'm not sure if you use the raise hand feature, I will see anything in this small overlay, but please just shout if you did. I actually see Mayank, you raise your hand or thumbs up. Thanks, at least one person. Orchid Core is also an open source project. A pretty cutting-edge ASP.NET Core CMS. So if you are a web developer, I highly encourage you to check it out. It's a community-driven project started by Microsoft a while ago, and it's constantly reinventing itself. It was one of the first ASP.NET Core CMSs out there. After being a pretty active ASP.NET CMS. And we are working with customers like Smithsonian Institution, Live Nation, even Microsoft itself. So a lot of US customers and customers from Europe and otherwise all over the world. I see that probably we also, okay. If you have any questions, by the way, we can also discuss it right away. Please, Mayank, let me know if there's anything interesting in the chat.
Sure, will do.
Thank you. But when we are not doing ASP.NET Core development, then we are doing research and development. And one of the cool projects there, I think, is Hastlayer. But let's not talk about Hastlayer yet. Let's talk about you first. And let's suppose that you are doing some number crunching. And by that, I mean some application, some algorithm in the following areas, like, as we also discussed before the talk, something like AI, machine learning, or something with pictures, image processing, video processing, computer vision, have a lot of things common, or algorithmic trading on the stock market, since we already talked about fintech before. Probably even high-frequency trading on the stock market, where every nanosecond counts. And I'm not exaggerating, indeed, every nanosecond counts. Or you are doing some heavy data compression, or perhaps something in the area of cryptography, perhaps with cryptocurrencies. Now, let's suppose that you want to make your app, your algorithm faster. What can you do? Well, the usual .NET cookbook. First, you try to figure out what's slow. So you profile it and you try to optimize the slow part. Let's suppose that you have already done that. Secondly, if the algorithm is suitable for that, you try to parallelize it. By parallelizing, I mean using the task parallel library for task level parallelism, pretty much multi-threading, or perhaps using operation level parallelism. Vectorization or single instruction multiple data are terminology that probably ring a bell as well. Let's suppose that you have already done that. And the third thing that you can quickly attempt is using, well, more or faster hardware, pretty much scaling up or scaling out. Let's suppose that's also something that you have done. What else remains? Well, the last thing you can do is use a different approach to computing. So if you have run out of hardware, or if you have run out of hardware feasibly, so you can't just simply throw money at the problem, then using heterogeneous computing is the next approach. So using other computing devices than a standard server with a standard CPU. Of course, GPUs is something perhaps everybody knows here. Video cards, that's one of the commonly used approaches today. Or we can use FPGAs. Now, what's that actually? Let's explore that part a little bit more. Did anybody actually work with FPGAs here before? I would be quite curious if anybody has. Please thumbs up or something like that. Don't feel bad if you haven't, because it would be very very unique in a .NET developer group. David, oh, very good, very nice. Can you perhaps also quickly mention what you have done with them?
Yeah, I was just going to say I did worked with them just a little bit in college, but that was 25 years ago. So
okay,
very, very different landscape now. So
yeah, but the basics are the same. And
right.
And seeing FPGAs in college is actually how I got into the space, because I'm the originator of the Hastlayer project, and that's when I say that, okay, there should be a better way of doing that. Because FPGA development is something else. FPGAs, or field programmable gate arrays, are pretty much chips that can be dynamically rewired, or as they call them, reconfigured. So if you want a processor that does some matrix calculations, you can configure an FPGA to do that. Or if you want to have an image processing processor, you can configure an FPGA to do that. It can be configured as an application-specific processor. How they, or why they teach them in college, is because they are very, very low level. It's logic hardware design, pretty much. But even if you haven't directly worked with FPGAs before, I'm pretty sure that you have used them in some way, even if you didn't know. For example, if you Google something on Bing, you have used FPGAs because Bing is accelerated by FPGAs. I'm not sure about the new Bing though. Azure uses FPGAs for software-defined networking. So pretty much anything you do in Azure will in some way flow through FPGAs. But FPGAs are sometimes also used in household appliances like routers, or not so household appliances like X-ray machines or self-driving vehicles. But as I mentioned, one peculiarity here is that it's hardware engineering. You have to be a hardware engineer to utilize them. Just to alleviate some confusion you might have, although FPGAs usually have a visible circuit board, like a GPU, they have nothing to do with a perhaps similarly looking Raspberry Pi, because a Raspberry is a small computer. Similarly, Arduino boards have nothing to do with FPGAs either. Those are microcontrollers. Although there are now FPGAs that are built together both with Raspberry Pis and with Arduinos. So why would you use FPGAs? Not talking about how they are used in chip design for kind of a hardware emulation, but when we are talking about hardware acceleration for software, because they have some unique computing benefits actually. So let's compare them with CPUs and GPUs. This will be some totally non-scientific comparison, just to give you an idea. Of course, everything here highly depends on the specific use case and the specific hardware. But let's talk about parallelism first. So how many things you can compute with a given device in parallel? The chart on the left. And CPUs, I think here, are pretty much on lower ends. So your CPU can have 4, 8, 64 cores, but that's about the hardware level parallelism you will get. On the other end of the spectrum are GPUs. GPUs are highly parallel devices. They have thousands of little processing cores. Now, those cores are a lot simpler than CPU cores, but still, if you are within the limits of a GPU, you can have thousands of hardware cores all running in parallel. Now, FPGAs are kind of in between, because FPGAs don't really have cores, although that's not entirely true, but still the hardware level parallelism you can achieve is in the order of hundreds. Okay, now let's see the complexity of programs, of complexity of algorithms that you can execute with these devices. And CPUs, of course, win here, because if it's a program, you can run it on a CPU. GPUs are on the lower ends this time, because the programming model is much more limited there. It's not that you can just run anything on a GPU, it's limited. And FPGAs, I think, again, are kind of in between, although you don't quite run a program on an FPGA, but the complexity of the algorithm, let's say, that you can implement with an FPGA is somewhere in between. And lastly, power efficiency. And this is where FPGAs really shine, because I think GPUs and GPUs are roughly on the same level here, of course, highly depending on the specifics. But FPGAs are a lot more power efficient. You can compute a lot more stuff with 1 watt of power. And the reason is that with an FPGA, it just computes what you need to be computed. There's nothing else. There's no operating system to run. There's no memory management. There are no other programs running. It's just what you need to be computed right there in the hardware. And power efficiency is, of course, cost, money. You can do the same computations with a much lower price. But it does come with a huge drawback, and that's that it's very hard to utilize FPGAs. David probably can also attest to that, even from 25 years, because it's very, very different from software development. Because, you know, everybody can program a CPU. Most of the people can achieve also programming a GPU, talking about developers. But FPGAs are something completely different. You are not writing a program for a processor, but rather you are creating a processor. It's hardware design. You have to think in terms of logic gates and clock cycles and wires. It's super low level. But with Hastlayer, we intend to bring the complexity down right to the CPU development level. So a lot of introduction. What is Hastlayer actually? It's a tool. It's an open source tool that takes a computer program and turns it into a piece of FPGA logic. We could also say that it takes a computer program and turns it into a computer chip. Otherwise, we take a piece of logic that was originally expressed in a software form and create an equivalent logic, which is expressed as hardware form. And of course, not just any software, any program. We are talking about .NET. And we are actually talking about .NET indeed, not just C#. Although, of course, usually we use C#. But in principle, any .NET compatible language can be used here, because Hastlayer processes the .NET assemblies. We actually have not just C#, but also an F# sample if you are interested in functional programming. So all in all, what we get with Hastlayer is the computing benefits of FPGAs for all of us software developers. So first of all, you can get a performance increase if your algorithm is massively parallelizable and compute bound or memory bound. Secondly, you get a higher power efficiency. So you can compute a lot more with a lot less power. And thirdly, it's just software development as before. So a lot of talk until now. let's actually see it in action. So I will now switch over to Visual Studio. Let me actually make this a little bit bigger. And what we see here, as you may have guessed from its name, is, well, a highly parallelized algorithm. This is not a real-life example. This is more like an exaggerated example of the kind of algorithms that are best suited to be accelerated with Hastlayer and with FPGAs. And this is something that we'll actually implement on an FPGA in a couple of minutes. What this algorithm does, the bulk of it is inside here. Well, it creates tasks, this many actually, 260, because this many will fit on an FPGA. What fit means, I will get to a bit later. And it starts 260 tasks, and within these tasks, it runs this this logic. It's pretty much some conditional logic which is executed 10 million times. So we are pretty much simulating some heavy lifting going on, heavy in terms of CPU-bound algorithms. And what happens after that is that we wait for all of these tasks to finish, and finally we sum together the outputs of all of these tasks, and that will be the output of our algorithm. Again, just a simple example to give you a feeling of what's the best suited for such hardware acceleration. And let's actually also run this. What I will show you, what I will use for this demo will be this little thing here. I thought that I will spice this up a little bit. And Hastlayer can be used in the cloud, like in Azure, but perhaps you didn't know that you, as a .NET developer, can also write software for satellites. Satellites, as in a spacecraft, because what I'm holding here is the same hardware that's also available as an onboard computer on a lot of satellites. Actually, it's not the whole thing. Because this is a development board that has also a lot of bells and whistles. The FPGA itself is right in the middle. This is not just an FPGA, but also an ARM CPU, and this runs a little Linux, a fairly standard Linux, and we put a completely standard .NET on it, and Hastlayer. So let's see how it works. Sorry. I'm now switching over to a terminal because I'm remoting in to this FPGA port, and I'm running a demo for you. What is that? What it does is that it's the same parallel algorithm that I've shown you. It first generates the hardware implementation with Hastlayer. After that, it first runs the parallel algorithm sample as software normally on this ARM CPU, which is, by the way, a 2-core ARM CPU, something similar to what you have in your smartphones. It's a bit slower because you can't really put a smartphone in space yet. And once the software execution happens, it also executes the same thing as hardware 3 times. So let's see the results. As we can see, when it was executed as software as usual, so on the CPU, it took about 25 seconds, 25,000 milliseconds. Now, let's take a look at the hardware implementations. If we scroll down a little bit, we will see that here it is. The hardware execution itself, so how long it took on the FPGA, it was around 240 milliseconds. And the execution time with the .NET G compilation happening the first time and the round trip from the CPU to the FPGA was around 300 milliseconds. if we take a look at the second run, then we see that, well, the jittering and all the initial setup time is gone, and we are down to about 250 milliseconds. So running the same thing as a hardware implementation was about 100 times faster. And I think it's about 120 times less power. So that's a lot of gains. Of course, this is just one example, and your mileage may vary. This highly depends on a lot of factors, but you see, this is something that you can achieve without much sweat. One more thing in Visual Studio. Until now, I've only shown you the algorithm itself. I didn't show you how we actually execute it, because how this works is that the rest of your software is just .NET as usual as well, and you can use this this hardware accelerated algorithm pretty easily. In this program class, I have a very basic approach on how to use Hastlayer, because what happens here is, well, first we create a Hastlayer shell, just that, and then we do some configuration. The most important configuration in here is pretty much telling Hastlayer that, hey, this is the class that I want to access from the host PC or from the host CPU. This is something that we call hardware entry point. Pretty much you tell Hastlayer which classes you want to call from the outside. And then comes the actual hardware generation. So this is the method call where Hastlayer creates the hardware implementation. You also have to pass in all the assemblies that are related. And finally comes the execution. You see, this is how we would do it normally. Well, without dependency injection or anything, just taking a look at the very simplest case. And this is how we do it with Hastlayer. We take our parallel algorithm instance and wrap it into a dynamic proxy. That's pretty much the one line that Hastlayer requires. And after that is just calling methods as usual. You see, we just call parallel algorithm run and 2 and 3 times. This is what I'm showing you in the terminal. You just call the methods as usual. All the communication between the host PC or the CPU and the FPGA board is handled automatically, and you don't have to care about it. Now, I've shown you how Hastlayer can be utilized from a consumer application and why you would do it, but I didn't yet actually show you how it works. So let's take a quick look at that. What I've used here for this demo is this FPGA board, what I've shown by the webcam as well, and the FPGA itself is that little chip in the middle. That's a chip that combines an ARM CPU and an FPGA. It's pretty much a system on chip. Why it's a little bit bigger, what I've shown you is because the FPGA board plugs into a motherboard. That's a development board that has Ethernet ports, a USB port, a port or a connector to a power supply. So it has a lot of bells and whistles for local development. But when you are out in the field, when you are on board of a satellite or a drone or in an embedded device like an IoT device, you don't actually need these. And one more thing. What's the magic that happens between Hastlayer processing your .NET assembly and the FPGA working? Well, let me show you. And I'm switching over to Notepad ++ actually, of course, and I'm showing you some code. you may notice that there are some familiar terms, packages, functions, begin if. Now, this is not Delphi or BASIC or anything like that. This is code, but this is hardware code. This is not a program. This is hardware that will be turned into pretty much a piece of silicon in the end. This is a lot of boilerplate that we have here. This is the code that Hastlayer generates. But if we scroll down a little bit, we'll see something familiar, namely here, parallel algorithm. So this here has to do something with our example. And this is not the whole thing yet. By the way, this whole block that we see here are just type declarations. It's not the whole logic of parallel algorithm, of course. But I'm showing you this because there is this 0. And if we scroll down, you see we have the same thing with 1. And a little bit more, we have the same thing with 2. Now, can you guess where we are going with this? Of course, if we scroll down a little bit more, now we are at the index 206. A little bit more, I hope to be able to actually find that. At the end, we have the same thing again with the index 259. Now, do you remember that in C# we started 260 tasks here? Now, when Hastlayer generates the hardware, we actually have 260 copies on the hardware of this logic, which is running in a task. So that's where the advantages come from. That's where the efficiency and the power increase comes from. We pretty much implanted a 260 core processor just for this class. That's why I'm saying that with FPGAs you get an application-specific processor. It just does what you need, but it can do this very efficiently with a very high degree of parallelism. You can't get a 260 core CPU. But you can create kind of a 260 core CPU just for this class. And that matters a lot. And it's not just performance, but also power efficiency again. So a lot of cost can be saved there. Okay, is there anything else interesting? One of the things with hardware development is that it's not like there's much abstraction. Of course, it's very low level. With .NET development, you write the code once and you can run it in a lot of on a lot of devices and a lot of very different devices, depending on how you have created it. But one thing that you can be super sure of is that you have created, if you have created a program, for example, for Windows 11, then it will run everywhere where Windows 11 runs. This is not the case with hardware development. You have to specifically support every FPGA chip and every FPGA board. What Hastlayer supports is a technology called Vitis by the biggest FPGA manufacturer, Xilinx. With that, it's a little bit easier because that's actually kind of an abstraction. It's not an FPGA, but in the development environments that we utilize behind the scenes for that. And the good thing is that because of this, Hastlayer supports high-performance hardware accelerator cards that are usually used in data centers, like in the cloud. Azure, for example, or AWS has such cards that Hastlayer can utilize. And also, we support these little devices that I've also shown you called Zinc, by the way, which is widely used in the aerospace industry. Again, on board of satellites and drones. So you may have not thought of yourself as somebody who can, with your .NET knowledge, write programs for space, but you can actually do that. And of course, today is the big day of the Starship launching. We have also done some benchmarks with the little things that I've shown you. We have seen 10 or 100 times better performance, and similarly 10, 100 times better power consumption. On the big accelerator cards in the cloud, it was actually worse, unfortunately, but still pretty nice advantages. Of course, these are examples and benchmarks. By the way, everything is detailed on GitHub, and all the code that I've shown you and everything else is up on GitHub as well. Your mileage may vary. It highly depends on your algorithm and also the hardware device that you are using. And also one cool thing, I think, has any of you here used other number formats from .NET than the integers? So, int, uint, short, something like that, or float and double. So anything apart from float, double, and integers? It doesn't seem so. Now, this is normal. So normally, you don't need to use anything else, especially because especially in .NET. But there are use cases like machine learning again, where the built-in and the standard number types just don't cut it. For example, in machine learning with neural networks, people are using reduced precision floating point. So not a double, which is a 64-bit number, not even a float, talking about .NET, which is a 32-bit number, but an 8-bit floating point number, because they don't need more accuracy, but for performance reasons, they need to keep these numbers as small as possible. And one of the things that you can do in .NET is create your own number formats. That's not something most of the people do, of course, but I think it's a quite curious thing. And with Hastlayer, what's even more interesting, you can get hardware support for it instantly. We have actually done one of these. There's a number type called POSIT, invented by a mathematician called Dr. John Gustafson, and it promises to be a lot better than the floats that we otherwise use. We have created a .NET library, which is a POSIT number format, a struct, and instantly with Hastlayer, we could create a hardware implementation for that. So pretty much, we created a new number type for .NET, and at the same time, we got a hardware implementation of it. Well, we got hardware support for it too. Now, what else do we have in mind for the future? We want to have a lot more use cases. So there are use cases, of course, that I didn't mention, just examples, but we want to see more examples of suitable use cases for Hastlayer out in the wild. This is why we also partner with the Wigner Research Center for Physics, because, well, scientific computations, scientific simulations is also an area where performance matters a lot, and FPGAs are already widely used. And be aware that FPGAs are already there in pretty much every cloud. As mentioned, AWS, Azure already have FPGAs. You can just go there and get a virtual machine with an FPGA in it. Also, the CPU manufacturers know that FPGAs will be important. Intel, about 4 or 5 years ago, bought the second largest FPGA company called Altera, and something like 1 or 2 years ago, AMD bought the biggest FPGA company called Xilinx. So they also know that they have to do something to keep up with performance demands, because Moore's law is pretty much over. Sadly, Moore itself has passed away a couple of weeks ago, and they have to do something else. So just putting more cores in a CPU won't work. You can't make the architecture much better anymore, especially if you want to keep backward compatibility. Of course, increasing the clock speed is not an option since a decade, or almost 2 decades probably. So there needs to be some other approach, and putting FPGAs into CPUs is quite an obvious way to gain some more performance, because then specific computations specific to your app can happen in a way that that there's direct hardware support. So to finish it up, before talking about any questions you may have, if you like this, and I really hope you did, please go on GitHub, check out the whole thing. I'm linking here to the SDK, what you would utilize normally, but all the other parts of Hastlayer are also up there. And be ready, because I think due to the mentioned reasons, FPGAs will become more and more important, and generally heterogeneous computing will become more and more important. So please get in touch with me if you have any further questions, or if you have a cool use case for Hastlayer. And also now, if there are any questions from the audience, I would be more than happy to discuss them.